Okay, let's go ahead and start the class. Today, as promised, we are going to uh, do an exam review. I'm going to solve some example problems. I have received a couple of emails about a couple of questions we solved in class and a couple of concepts, so I make sure to include those in the exam problems as well. Let me just clean the board. Should be good to go. So, just to make sure we're on the same board, same page, we're all on the same page. Your exam is going to be on Wednesday. We have talked about this, right? And you're going to get 10 descriptive questions, a combination of MCQ descriptive questions with just one-line descriptions. And undergraduate students will get 3 problems to solve. Graduate students will get 4 problems to solve. So 1 additional problem. Everything else will remain the same. And students who are taking the class online, I would rather if you take the exam at the same time as the other students in class students, but there are a couple of people, as I said, I've mentioned in the previous lecture, there are a couple of people who can't do this. I will work with you on an individual basis. So make sure not to talk to any online students about the exam after the exam. But there are a couple of them who need to take it. There is one student who is going to take the exam tomorrow. I don't remember who it was. Yeah, but we have talked over email, so don't share the exam problems with the others. And yeah, I guess we talked in detail about how the exam is going to be conducted. It is an open book. Oh, yes.
Could you make the recordings of the lectures available for everyone?
They are available for everyone on YouTube.
Okay, on YouTube.
Yeah, on YouTube, yeah. Yes, we have actually one question here. Can you repeat the one that who is taking the exam when and through what medium? So you are having one question about the exam here. Who is taking the exam when and through what medium? So if you are an online student, you will take the exam on Blackboard. I will create an exam portal, test portal. You probably have done this before. This is our 3rd semester into the pandemic, so I'm pretty sure you're familiar with this. If not, let me know, and I will probably do some tutorial. But the exam will be posted on Blackboard if you're online, and at the same time as the other student. If you have registered with SDRC, which I can't think of anyone who already has, and it's a little too late to begin the process, you would get time and a half for your exam, which I think we don't have anyone in the class who qualifies for that. So everyone will going to get 75 minutes. The good thing about taking the exam in class with others is that if I extend the time for everyone in the class, you will get the same benefit if you're taking the class online. But if you do it at another time, I probably cannot give you any extensions. Okay, any questions, concerns about the material, about the exam? Yes. Open everything. Open Google, open everything.
Oh, awesome.
Yeah. You can bring in your laptops, do whatever you want to do. Of course, you cannot like FaceTime with your friends to solve the problem. But I guess I'm going to be here, so. Yes.
You said open Google?
But what I mean is you can bring your laptop and Google whatever you want to Google.
What is the limits on
No limits. The reason is that I've made the exam essentially open everything is because I don't have any control over online students, right? So it's going to be unfair to all of you to have one policy for you that I cannot follow up on with the online students, right? But in usual, my practices, I only allow one exam, one equation sheet. So one. Okay. So no other questions. Okay. So let's begin the example problem solving part of the lecture. Yes, we have a question here. Will the time be limited on the Blackboard, scanning and submit? So if you're taking the exam on Blackboard, you'll probably get 10 minutes for scanning and submitting your exam. So 75 minutes plus 10. And okay. So I received an email, and also someone came to my office and asked me a question about one of the examples we briefly mentioned in class. What was the example number? If you give me a page number, we can go over. Yeah, example 1.1. Yeah, that's the first example of the book, example 1.1. We are told that we are in a supersonic flow. We actually solved this problem. I don't know if we solved it completely, but we are going to attempt the solution one more time. So we have a supersonic flow over a 5-degree half angle wedge. Half angle, we have a wedge with 5 degrees half angle. And a supersonic flow is coming. It is flowing in a supersonic flow. The frequency Mach number is 2. And the pressure and density is P infinity 1.01 10 to the 5 pascals or newtons per meter squared. And density is 1.23 kilograms per cubic meters. Okay, the pressure on the upper and lower surface of the wedge are constant with distance. So your pressure distribution looks like this, just a uniform distribution. And they are equal to 1.31 newtons per meter squared. The shear stress over both upper and lower surface is given with this formula. Let's say this is your wedge. And shear stress is going to change like this. So tau wall is 4s to the negative 0.2. Yeah, sure. Yeah. The chord length is 2 meters. And we want to calculate the drag coefficient for the wedge. And S is this distance on the upper over the lower surface. Okay, so we are at the 0 angle of attack. Okay, so the chord length and the flight path make the 0 angle with 0 angle of attack. And the first question I want to ask you, or the first thing I want you to think about, is what is the lift coefficient here? Who can answer that question?
0.
0. Why?
Because there's no angle of attack and it's symmetrical.
Okay, exactly. So it is a symmetrical shape. 0 angle of attack. You're going to get 0 lift. You could actually look at the pressures. You have the same pressure on the lower surface and the upper surface. The components in this direction, in the y direction, would cancel each other out. So PU minus PL would have been 0. So lift coefficient or lift would be 0. We are doing a 0 lift one. Okay, but what about drag? We want to calculate drag. There are 2 components here. Something that I think we forgot to mention here. There is also pressure exerted on the back, which is going to be P infinity. CD is what you want to find out. Okay, so how can we find the drag coefficient? We have to look at the forces in the x direction, right? In the direction of the flight. What kind of forces do we have? We have a component of pressure force. We also have the shear force. Okay. We also have the shear force. So you essentially don't need to even use the formulas you already have. As long as you understand you have to write the force balance in the x direction, find the total of the forces that is being exerted in the x direction. And so let's put the integrals aside. Let's do this. Let's just do the force balance. What are the forces? The pressure forces. We have uniform pressure distribution on top and the bottom. Both of them have a component in this direction, right? But what is that component? Again, drag is the force in this direction, right? What is that component? How can we find the component of pressure distribution on the upper surface and lower surface in this direction? Exactly. So your pressure, let's do pressure first, then we will convert it to pressure force. Is going to be your pressure multiplied by sine of phi, right? That's the pressure component in one direction for the upper surface, right? And to have a closer look here, I received actually one question about the angle. The angle in this direction is positive. That's the sign convection for the angle. And this in this direction is going to be negative. Okay? And we want to find the component of this force in this direction, which is going to be P sine of phi. What about this one? Is going to be P sine of negative phi. Okay. How can we convert this P sine of phi, the component of pressure, to force? How can we convert this is a component of pressure, right? It is not a force yet. And pressure is force per unit area, right? I want to not convert. I want to transform this to the force. I want to calculate the force that is generated because of, that is exerted on the body because of this pressure. Does it make sense? Okay, how can I do that? Multiplied by the area, right? So it's a uniform distribution, right? Because it's a uniform distribution, your total force is going to be this component multiplied by the area. So PU sine of phi multiplied, one thing that you need to keep in mind is that this P is in the negative direction. So we're going to get the negative here. But eventually these two will be added. Sine of phi multiplied by your A, whatever your A is. Since it's a two-dimensional analysis, we are going to assume unit depth, right? So one in this direction. And what is the area? What is the length that, what would be the area? With the unit depth assumption, what would be the area here that this force is operating on? Okay, exactly. So, yeah, exactly. So this S, this length, multiplied by unit depth, which is 1, right? This is the force that you are exerting. This is the area you're exerting your force here. So S multiplied by 1. What is S? How can we find S? We have this angle here. And we also have this length L. C is 2 meters, right? With having this angle and the C, can we find the S? Yes. How can we do that? Cosine phi, exactly. So cosine of phi, 5 is equals to your C divided by S, right? So S is going to be C cosine of 5. So your force is going to be PU sine of 5 multiplied by C cosine of 5. And then we're going to have the same thing. And there's a negative sign here. And C cosine of negative 5 again. So let's plug in the numbers, and I want one of you to do these calculations for me. Is there anyone who has a calculator? No one. Okay. One person. Thank you. So just yes.
I might be dumb here, but wouldn't the cosine, wouldn't S be equal to C over cosine?
I'm sorry, that was my mistake. That was my mistake. I'm sorry. That was my mistake. I'm sorry. Thank you. Yeah. I won't lose any points if I do these kind of errors, but you will. So make sure not to make these type of errors, which are very common. Because of the direction, essentially, let me put it this way. These negative signs and positive signs are just convention, right? If you just look at it here, these two forces have to be added together, right? So whatever you want to do with the signs, do it and add the forces together, right? These are just conventions. The reason I added the negative sign on the upper one is because it is in the negative direction of your y, right? So it's essentially a negative vector. Yes. That's S times 1. S times 1, whatever that S is. Okay, so can you make this calculation for me? 1.31 10 to the power 5 multiplied by sine of 5 multiplied by PU multiplied by C, I'm sorry, multiplied by cosine of 5. So, and multiplied by 2, essentially, because we have 2 of these components. What is that value? We actually may have it here. Yeah, please. $45,000. It shouldn't be 45,000, but let's do 45,000. That's all right. The final number. Okay. So let's do the pressure forces. I'm gonna use F of P. Pressure forces exerted on this body by the upper and lower surface are going to be, let's say, 45,000 newtons, right? We know how to calculate this. Is there any other pressure force here? Not shear force, pressure force. Okay, the one that is being exerted on the back, right? What is this length here? We have this 5 and we have this 2, right? So how can we find this length? What is the tangent of this 5? This, let's call this length, right? So tangent of 5 is going to be equals to L over C, or 2. So your L is going to be 2 multiplied by tangent of 5, right? And then this whole length is 2L. Okay, we have the length now. And pressure, we also have the pressure is going to be equal to P infinity, 1.011 10 to the power 5. Okay. So what is the pressure force in the other direction? We have the pressure, it's a uniform distribution. We also have the area. What would be the pressure force? Pressure times the area, right? So an area, it's a unit depth. So your area is going to be essentially 2, your L is 2 tangent of 5. And this length is 2 times your L. So 2L is 2 multiplied by 2 tangent of 5, which is 4 tangent of 5, multiplied by 1 will be your surface area on the back. Then you multiply it by your pressure, which is going to be 1.01 10 to the power 5, whatever that is. These are in the opposite direction to each other, minus whatever the value that is, like 4 tangent of 5 multiplied by 1.01. You're going to get the pressure forces. Okay? So that's one component of drag. Yes. That's 2L, yeah. No, this itself is 2L. Okay. So we have the pressure forces that is going to contribute to the drag. And keep in mind that we are dealing with pressure force per unit length. So we're going to do F prime. Because we are assuming unit depth here. Okay, what are the other forces that are present here? What are the other forces that can contribute to drag? Of course, we only have one other force. that is present here is the shear force. So how can we calculate the shear force? We have the distribution of the shear stress over the wall. Okay. At this time, it is not a uniform distribution. So how should we deal with that? The only way is to take the integral. Okay. To find the total shear force. So this time, there is no escape from the integral. We have to take the integral. So let's go back to your notes and tell me what is the equation we use to find the friction drag. We have this friction. We have the shear stress distribution. We want to find the equation. Let's go. I see a lot of people are not going back to their notes to find the equation. Okay. Anyone?
These normal and axial force equations?
We can definitely use those, right? Yes, we can use those as well.
Which
But
one are you looking for? Equation for the shear stress.
okay, let's use yes, this is the actual. So this is what I'm looking for. But I wanted to have a more general. What is that equation?
But yeah, actually,
Yes, the actual force is your drag force here, right?
negative PU DSU sine of theta plus tau U DSU cosine of theta.
Okay, what about the lower surface?
For the lower surface, it is PL DS sub L sine theta. That should be the first term should be negative in that as well. Sorry.
Okay.
Wait, no, it's not. No, it's not. No, it's not. I'm great. The second one is tau sub L DS sub L cosine theta.
So we have already taken care of this part, right? Since it was a uniform distribution, we then need to write the small element of it and take the integral. But for this one, we do need to, for the second part, we do need to take the integral. Why? Because it has a distribution. So what is DSU here? Okay. And how can we relate it to L? Because we want to find, or C. Let's do X. X, Y. We want to find the force in this direction, right? So we are already finding the components of tau with multiplying by this cosine of theta. But what about DSU? For the upper and lower surfaces, your DSU, what is DSU? How can, or in terms of X? I wanna present DSU in terms of, again, let me repeat this. We are looking to find the forces in the x direction, right? Actual force, which essentially, since the angle of attack is 0, we are finding the drag force. How should I take that integral? Let's say this is something that you want to do in the exam, right? How would you do so? How would you take this integral? Do we need to? We don't actually. Yes. Okay. Let's do it. Let's actually apply this here. We have 2TU, right? Which is equal to 431 S. We actually don't need to DSU, which is equal to DS, right? DS on the upper surface and on the lower surface are the same. This will be your upper surface. For the lower surface, the same thing. Can we take this integral? Integral of whatever that is. Yeah, sorry. Cosine of 5. Cosine of 5. But that's just a number, right? Can we take this integral? Yes. How do we take the integral? What is the solution to this integral? S to the power negative 0.2 ds. Okay. So what would be the solution then? You are very close. Okay, so divide by 0.8. Yeah. Okay, thank you. So this will be the solution to this integral. 431 cosine of 5. Okay. So, but the other part would be we have to find the limits of this S. S, let's say this is the start of your coordinate system here. S goes from 0 to what value? What is the value here? What is the point here? It's going to be C divided by cosine of 5 again, right? So just plug those two numbers in there. 0 and C divided by cosine of 5. You should be able to find this part of the pressure force. That's only for the upper surface. Do the same analysis, which is going to be the exact same analysis because the distribution is the same, ds is everything is the same. And you multiply it by 2. You will be able to find the shear force, right? Is this clear? Okay, good. And then you just add them up to find the total drag. Drag by shear, shear drag, drag by pressure. Okay. But we are looking for drag coefficient, not the drag. How can we find the drag coefficient? Again, if you recall, drag coefficient is a force coefficient. How did we find force coefficients? We divide them. We divide the force by the dynamic pressure multiplied by your area. Here, since we are making this unit depth assumption, this will transform to d prime, and this will be C. Do we have Q infinity? Yes. As 1/2 rho V infinity squared. Do we have C? Yes, it is 2. Do we have D prime? Yes. Should be able to solve it. Okay. Is this clear? Yes.
How did you know that the area was S times 1 then?
That was by definition. That it's a 2-dimensional geometry. we actually, what we did, we removed the depth essentially, right? That's why we are dealing with d prime. We are dealing with force per unit depth, right? That's the idea of the two-dimensional analysis. You are always assuming that your depth is unit. Yes. Can you speak up? Okay. So this is when you are integrating. This is from S1 to S2 tau u cosine of theta dsu, right? This was the integral. But we essentially put the limits of integral after we did the integration, right? So this will be whatever the solution to your integral is. Let's call it A, whatever that is, from S1 to S2, right? Just plug in the numbers. Does that answer your question? Okay. So, okay. If there is no other questions, yes. I'm sorry, this camera disconnected. I can't hear. I just I'm very distracted now. Let me just fix this. Okay, what was the question again? That is correct, yeah. Yes. Here. So essentially, this is pushing your a slender body forward, right? It is acting in the opposite direction to drag. Okay, but where did we talk about wave drag? It's just a pressure distribution at the back, right? What is wave drag? Wave drag or wave drag? Wake. Okay, wake drag. Okay. Why do we have? Let's actually why do we have a drag created by the wake? Due to the pressure difference, not pressure, right? Pressure difference between front and the back. What you're saying is actually doesn't make any sense physically, right? There is no way we can have pressure on this surface in the other direction. Pressure is always normal to a surface and pointing inward, right? It either can counteract the pressure inside, and then you will get just your body will be destroyed, right? Or it cannot. Generally speaking, pressure here would be higher than the pressure here, right? That's why you will get the drag, the wake drag, whatever you want to call it. Okay, but the pressure will be in this direction on the back. It will be a lower pressure, but it will be in this direction. Okay. Okay, so we have lost the video feed for whatever reason here, so you just have to bear with me for a second. I guess I don't know what to do. Just bear